Okay. So I just posted the link to the slides for today. I'm going to post it again. I edited the message. I'm going to post it again in the thread. We call them slide decks. That's from back in the day when we used Google Slides, but it's really a markdown file. That's just a link to the GitHub where you can go follow along through the class material for today. So today we're going to be talking more about for loops and accumulators specifically. I'll give you all a second to open that up while I'm getting my screen share up and running. Okay, cool. So I do want to do some review of mutability. I'm just going through and kind of trying to collect the concepts that we've covered and things I want to circle back on here. So I want us to have a little bit of review on range. There's the whole range and slicing with the whole start, stop, step thing going on. Concatenation. Let's see. We want to review mutability, although I'm just going to cover that again, basically. Cool. I'm going to try to do an overview as fast as I can. I suspect y'all are mostly tired of seeing me go through this. But I really want to make sure it's sort of ingrained, you know, just so you have a sense of how to categorize the things that we're learning, so you can kind of know the roles that each thing plays, so you can have a sense of how everything fits together and what everything does. Abstraction, control flow. Data types, we've talked about int, float, bool, none, string, list, to some extent range, although range technically is its own type, but we just kind of think of it as a function that returns a range. It's a little bit different than the others. So related to list, I'll say range, kind of adjacent to lists. Abstraction, functions, variables, do those in the other order. Control flow, we've got if, elif, else. Other things involved in control flow, equal, not equal. What am I doing? Less than, greater than, less than equal, greater than equal, and or, oops, not do them in the order of operations. What else we've got for control flow? In element in list, right? So that check for membership. I'll put that down here too. Okay. Iteration, we've talked about for loops. We're going to talk more about that today. Oh. There's about a 1-inch gap where it is possible for the sun to be and shine directly in my eyes, and that's exactly where the sun is. It's extraordinary. Okay. Let's move on. So there's your overview. Here's where we're going to be focusing again. We're going to do a little recap of this. And we've established for loops fairly well, so we might go really quickly. We may even get into the next slide deck today. Who knows? Anything could happen. Cool. I want to do a little 1 to 3 kind of exercise on all these things. I'll give you prompts. Don't do 1 to 3 just yet. Yeah. So let's do 1 to 3 for range. One to three, how are you feeling on range? Okay. You can tell I want to kind of cover range a little bit. So we'll talk about range a little bit today. Back to lists. Let's do a thumbs up and thumbs down if you remember concatenation from strings. Real quick. Concatenation, thumbs up, thumbs down. Double thumbs. Did you invent concatenation? I'll assume yes. Everybody, okay, all right. We'll do a quick one on this. It's an easy, it's a big word for a very straightforward concept. You'll probably, if you don't remember, you'll probably remember. I'm calling it indexing. I keep trying to call it subscripting. Um, 1 to 3 on subscripting and indexing. So you have a list and you want to retrieve a specific element. You put the square brackets after the list, put the number in. How comfortable are you doing that? Strong start. 1s and 2s are welcome. I do want to know. I should see if I can put a poll in Slack for these kinds of things, because that would actually be more useful in cases like this. Okay, cool. Thank you. Slicing. Seems like people are, I'm seeing, I didn't see any ones, I don't think. Sorry. I think people are basically okay with it. So let's talk about slicing. 1 to 3 on slicing. How are you feeling about it? 1, that's fair. Okay, a little lower here. That's all right. We'll cover that. Checking for membership, that's using the in keyword, in. Checks for membership, how are you feeling? 1 to 3. Okay, I'm thinking mostly 2s on this one. Okay, this is another simple one. So this one we can kind of go quick on as well. Let's get the easy ones out of the way. I'm going to use indexing and subscripting. Seems like people were pretty strong on that one. So we'll go for checks for membership and concatenation. I'll talk about slicing and range, and they're a little bit similar, but it seems like people are basically okay here. So I'm going to just kind of take that as basically you get the idea of how it works, and just we'll get some more exposure to kind of solidify that as we go. Okay, so checks for membership. If I have a list, let's say I have a list, which I do. And I want to see if some element is in the list. Okay, let me see if I can spell element. E-L-E-M-E-N-T. Good, I did it. So I want to see if this element is in the list. Simple as that. Now this gives me back, who remembers what this gives me back? Just give me back a list. Or an integer. Or a string. Or a bool. None. Yeah. Cool, yeah, people got this. All right, so if I try to see if hello is in the list, that's going to give me back false. That's it. That's checking for membership. You just have some, obviously I'm hiding these under variables. We could do it that way. I could say we could do the literals directly. Right, all of these are exactly the same line of code. They might look a little different, but list evaluates to the list, element evaluates to the hello, right? Of course, if I change element to something that is in the list, like 5, then that's going to be true. It's simple. So that's all a check for membership is. It just means we can use the in keyword to see if something is a member of that list. If you were like less than a 2.5 when I asked for a 1 to 3 on this, if you still have questions, if your number, put in your understanding 1 to 3 at this point, if you were like less than a low 2. If it's still a 1 or 2, that's okay. I do want to know. Okay. Okay, cool. I'm seeing all 3s. So yeah, this is almost a bigger, fancier sounding name than a concept this straightforward deserves, right? It's a nice and simple one, but no worries. Like if you were confused about that, it's all good. Concatenation. So we talked about concatenation with strings. It's a big word for a simple idea. If I have the string hello, I can use the plus operator. You may already remember where this is going, to add it to other strings. Oh, that's got to be a string. and let's just say I'll just do this, print A. Okay, so I have a string hello. I'm saving it under A. B is equal to hello. Oops. It's equal to A, which is hello, plus a space, plus world. And I'm going to print A and B just so you can see, doing this concatenation didn't make any change to A. A is still A, right? And then doing that concatenation just sandwiched those together, added them together, concatenated them together, and that's the value of B now, right? B isn't some weird string that has different parts to it. It's just one regular string, just as if I had a string that just said hello world, just like that. So nothing fancy there, it just turns into a regular string. Let's do this. So give me an update. What is if you had below a 2.5 on concatenation, we're talking about lists. Scratch that. The same thing is true for lists. We can concatenate strings to strings. We can concatenate lists to lists. And let me show you how that works. So sorry, I got a little ahead of myself. Apologies. So let's say I've got, I don't know, this list. Why don't I concatenate it against, call this list 1, and we'll call this list 2 equals list 1 plus this. And let's just print list 1 before and after, right? So you can see list 1 before and after the concatenation on list 2, it's the same. And list 2 is just both lists added together. They just extend each other. So yeah, that's how that works. Quick 1 to 3, how are you feeling on concatenation? 3. If you've got any questions, no worries. Great. Why space in the middle? Let's try it with no space. So I get hello world with no space. Like that. Right, I could add a space here like that into world. It does the same thing. But just since we were talking about concatenation, I thought, well, why don't I concatenate a few strings together just to show that, you can kind of put as many strings as you want together in whatever order. It doesn't have to just be 2. I can string a whole bunch of strings together by concatenating them. So, okay, so I'm seeing 3s and 2 8s. Good, thank you. Let me know, give me thumbs up if that answered your question. Thumbs up on Slack. Or thumbs down if it didn't. Okay. Great. So we covered check for membership and concatenation. Okay. Slicing and range are the big ones left. Why do I do this? I'm just going to comment everything out. let's grab a list. So it's not uncommon that you'll have a list and you want some subsection of that list. So let's say for whatever reason, I want this sublist of 387, right? So I can use slicing to tell this sublist where it should start, stop, and what, the increment should be, what the step should be. So I want this 387, so that's just, I need to tell it to start where this 3 is, end where this 7 is, and this is going to be a step of +1. So to do that, I'm going to say list sub whatever the index of 3 is, that's going to be 0, 1, 2. And we're going to tell it somewhere to stop. So let's tell it to stop at 0, 1, 2, 3, 4. If I tell it to stop at 4, it goes up to but not including that upper bound. So I could do 4 plus 1. Of course, I know what 4 plus 1 is. It's 5. I'm not printing anything. Print sublist. We'll see our output. 387. There's 387. Let's say I want 375, right? So I might do, I'll just go all the way to the end, and I'll do steps of 2. That'll give me that 375. Of course, I could have it end on that index of 5, right? So somebody reminded me yesterday, I forget who, somebody reminded me, reminded me by asking, do these have the same defaults, start, stop, and step as range? And they do, actually. So if I leave the start out, it'll start at the beginning. If I don't specify something for start, it will start at 0. If I don't specify something for step, it will actually go to the end. Excuse me, I keep saying step when I mean stop. Sorry about that. If I leave out a value for stop, it'll go to the end, which is actually described by len list, the length of the list that I'm indexing into. If I don't put something in for the step, it will assume that I wanted a step of +1. So that a step of +1 is going from left to right in increments of 1. So there you go. That's sublist. So what's funny is this, or since that's redundant for just doing this, this kind of segues into something that I'm going to cover here, which relates to mutability, which is copying. This is a de facto copy. There's other ways to copy. There we go. Okay. So all of these are the same. So I know there's a little bit going on with slicing. I'm kind of not expecting everybody to be at a 3 just from this little bit, but hopefully that's an improvement. Yeah, why don't I do this? That's better. Okay. So here we've got our initial list. We'll print it off. That's never going to change. We got kind of a long form copy, which is the same exact thing as this copy. I'm just going to delete that since it's kind of silly. We've got this copy here, and then we'll print off the list and the sublist. Okay, so here's the funny thing. We talked about IDs. So we know these values are the same. Are the IDs the same? I'm segueing into talking about mutability. I still need to cover range. The IDs are different IDs. So let's come back and explore why that is. In a second. Let's really quickly talk about range. So most often when we use range, we use it in a for loop. We'll say for I in range. And then we have to describe the range. So range's job is to return a series of integers from a starting point to a specified stopping point in a step of whatever. So if I give it one argument, so it takes start, stop, and step. If I give it one argument, okay, how do I put this? If I give it one argument, what is the type? What is the type of that? What must the type of that argument be? And which of those three start, stop, and step parameters does that argument represent? And what are the assumed values for the other two that I didn't explicitly pass? Okay, all right. Here, I'll do this. I should make this a formal breakout. I'll put a couple minutes on the clock for this. Feel free to copy, paste that your answer, and then you can just put in, for the type, whatever the type is here. Then the defaults here and the name of the parameter here. Or whatever. All right, about another 20 seconds-ish. Okay. Go ahead and get in your answers. Whatever you've got is fine. Okay, so range for any of its three arguments, whether it takes 1, 2, or 3, whether you give it 1, 2, or 3 arguments, always, always, always takes an integer. Doesn't take a float, doesn't take a list, takes an integer. So we have to make sure we're passing an int to range. When we pass it one argument, the parameter that that one argument will correspond to will be the stop. So that'll tell us where we want the range to stop, and it will assume that we wanted the range to start at 0 and go in steps of 1, steps of positive 1. Just like the same assumptions for slicing, for the sections of slicing a list. Start, stop, step. Cool. If we pass it, so that's for one argument. So if I do range 10, and I'll just print I here, we'll see 0 through 9, right? It assumed we wanted to start at 0, and remember, we go up to, but not including, just short of the stopping point. If we wanted to include that stopping point, we increment it by 1. There we go. What about if I do a start? So let's say I want it to start at 5 and go up to and including stop. I'll make this one a multiple choice. Meh, not like that. Start or stop, or stop, stop or start. Which is the correct way? Oops. I didn't even give it to you in a formatted code cell. There we go. Number 1 or number 2? Cool. Okay, yeah. Awesome. So that'll be, if I give it 2 arguments, it'll be start and stop. And I won't mess around. If I give it 3, it'll be step. So 5 to 10. 5 to 10 in steps of 2, 5, 7, 9, 3, 5, 8. -1. Meh. It's kind of an interesting thing. If you try to do a negative range, you end up with what's called an inverted range. Sometimes this can happen. Say if you you can get an inverted range, which is where the stop essentially stops before the start starts. So if we did stop and start, we've inverted the range. So it means it's going to start at 10 and go to 5 in steps of +1. So there is not a way to +5 starting at 10 going up. You have to go down, right? So this is going up. So what happens is nothing. You don't get an error. Nothing weird happens. Well, it might be weird that nothing happens, you know, so you have to be prepared for that, perhaps. So that's an inverted range. If I don't invert the range, if I have a regular range and I do a negative step, then that inverts the range the other way, right? Because essentially we're saying start at 5 and go up to 10 in steps of -1. So go to the right by going left, and since either direction goes forever in either direction, you know, we'll never get there. If the number line loops back around, I don't know about it. So I think that's yet to be discovered. So yeah. We can make a reverse range if we do something like 10, 5. This is always a little funky. 10, 9, 8, 7. So I think I wanted to do 5. Do I want to? Oh my gosh, am I doing -1? I don't know. Yeah, okay. I guess I need to do -1 if I do that. So if you ever need to do a reverse range, it's a little funky, but you have to do a step of -1, and you know your start has to be high and your stop has to be low. Thankfully that doesn't come up that often, but there you have it. You've seen it. Okay, cool. We're going to be using range a lot today, so if it's still a little foggy, don't worry about it. We're going to get so much practice with it, I presume, in the for loop material, and I'm not going to worry about it too much. I want to cover mutability and copying really quickly, and then we will get into the actual loop material. Okay, so mutability. The contents in a list can change while the ID of the list stays the same. Two lists that contain the same values that are not the same list will contain different IDs. So here's the thing. Let's do this. Let's say list equals list of 1, 2, and let's call this list A, and we'll call this list B equals list A. Now I'm going to say list B dot append 3, and what happens if I print list B? It's going to have 3 on it, right? What happens if I print list A? Is list A going to have the same contents as list B or different? Same contents. Somebody's voting for difference. What's your intuition tell you? I'm not seeing a whole lot of answers. That's okay. I mean, it's kind of a brain scratcher, right? But yeah. And let's think about this. Let me change this a little bit. I know I'm trying not to like just give you a question and then change the terms of the question while you're answering it, but like, are the IDs going to be the same or different? Same IDs, different IDs, same contents, different contents. Different as in different memory location? That is the question. Same IDs, okay. We've got a bit of a myriad of answers here. Weird question. Is list B just list A? What do you think? Are they literally the same list, or are they different lists? I'll just make you think about that. So if I run this, now, right? Same contents, right? So notice I modified list B, and list B changed. Sensible. It's what I expect. But list A also changed. Now, the way I said that is actually wrong, because there is no separate list A for there to be an also to change, right? There's not also a list A and a list B, right? There's one list, and that one single list, and I can prove that it's one list because the IDs are the same. Since the IDs are the same, they are the same freaking thing. So since there's one list, this one list has two identifiers. And that's a little bit of a problem, because you might have thought, okay, well, let's say I've got my initial data, and I don't want to really mess with this too much, so I'll just make a variable for like test data, so I can mess around with it, and I'll just set it equal to initial data, right? So this unfortunately does not make a copy of initial data and give you the values. This just points the test data ID or identifier at the same exact object. So sometimes you'll hear people say that variables in Python are pointers. And this behavior describes what that is. If you're familiar with what a pointer is from another language, Python variables are pointers. If you're not, we don't really dive into what a pointer exactly is, because the only kinds of variables Python has is pointers, and this is the behavior. When you assign something in this way, you just point that identifier, that variable name, at that object. So it's a pointer to that object, rather than like creating a different memory address for that variable and then like loading in data into that. So it's important to know that about that behavior. So you will often want to copy information, usually for the sake of having an original copy that you didn't alter, and then having a copy that you are permitted to alter, right? So in order to do that, in order to do that, we want test data to be a copy of the initial data. So let's say initial test data equals initial data dot copy, just like that. So notice now when I append to test data, which was formerly the list formerly known as list B, when I print out that ID and that list, it's a different object than the original one, than the initial data. So it only, this append only caused an alteration to this one that it was called on, right? So now we have two lists in memory. They point to the same point in memory. Yes, it's the same. List B is just a pointer to list A. Is it effectively just a name change for the list in this case? No, it's like, it's like a, I don't know, like an alter ego. Like it's one list that has two identifiers. We could just keep assigning variables to the same list, and then we could just have like, I don't know, however many 9 or 10 or 1,000 variables pointing at exactly the same object in memory. But hopefully it's obvious that that's not a good idea. More like, let's see, why is it beneficial to keep the initial data intact? It depends on your problem. I'm trying to think of an example here. Let's say you have a list of objects, or a list, yeah, like a list of um, client records that's gonna like populate some fields in an application, like a spreadsheet kind of thing or something. You have like name and maybe client location or um, information, I don't know, date of birth, whatever. And you want to do some transform on that. You want to like process that in some way. And the way you want to process it, it just makes sense to like pull in that list and start messing with the list. I've shown you append here, but there's a lot of other methods, and we're going to go over them in a probably in my next class. There's a lot of other methods that will change a list in various ways. Sometimes you're deleting things, sometimes you're moving things around, sometimes you're overwriting information, sometimes you're putting new elements in the middle, sometimes you're taking other lists and like kind of concatenating or extending that behavior with lists is often called extending one list by another list, right? So there's a ton of different mutations that you can do to a list, right? And it might make sense, oh, it's really easy to just like, you know, fiddle with this list, but if you've got if that list is already being utilized by something else that relies on it being in that state, you probably don't want to change that list. You will probably want to get a copy of it and then mess with the copy. So that's the idea. What is in memory? In memory depends on the box that we run the program in. I mean, sorry, I don't, oh gosh, I forgot exactly the context that I said that in. I know I've been throwing that term around. I mean, when I say in memory, I am talking about your physically your computer's RAM. Um, so if you don't, I'm not going to get too much into like hardware stuff, but like there's each RAM register is fairly complicated in construction, but fairly simple in its conception. It's a simple idea, right? You just have this vast, vast array of ones and zeros that can be turned on and off. There's no logic or processing happening there. It's just a buffer that holds states that can change from 1 to 0 quickly. So a program's memory is the like physically where those ones and zeros exist in your RAM is what I'm alluding to ultimately. So when I say like, you know, these objects exist in memory, You know, when we run this program, this data gets loaded onto your RAM somewhere onto your RAM, and each byte of your RAM represents some part of that data, and there's different ways that the RAM is sectioned off, and you know, your CPU will kind of organize things on it in a particular way, you know, so that's kind of what I'm alluding to, and it's a whole other can of beans. I don't want to get too much into the weeds of the hardware, but it's interesting stuff. So sorry if that was a bit of a jump for some folks. I know I just kind of dive into that. So we've got a lot of good questions. I appreciate the questions. Let's see. If you only have 4 gigabytes of memory and you're working with a 1 gigabyte data set, would you want to separate locations? Would you want 2 separate locations for the same data set in memory and RAM? Yeah, so this is a good question, right? Like, depending on your limitations, copying may be pretty expensive. I have 40 gigs on this machine, so, you know, and this is a little laptop, but you know when you're doing like big data work, you're often running your code on like an AWS instance, and if you don't have enough resources, you just shell out more money and you get more resources. So yeah, often the solution is add more resources. So unironically, the answer to your question, the solution to the question you posed, is you get a computer with more than 4 gigs of RAM. In reality, that often is legitimately the solution. Now, in absolute terms and more academic terms, yeah, you know, like if you know you have a constraint on your hardware, then you might not want to do that. Languages like C and C++ that were, you know, revolutionary in the early 80s put a lot more emphasis on in-place operations and mutation than a lot of modern languages do, because memory-intensive operations back in that day were expensive. Memory was often a bottleneck. It was often the first thing to limit your program's capacity was your memory. Of course, computers were also a lot slower. There was a lot more bottlenecks. You know, obviously technology has grown significantly since then. So, but yeah, potentially memory could be an issue. But I'm even thinking about it, like, what would it take for me to get, you know, I guess image data can be pretty hefty. So yeah, there definitely can be data sets where that can be pretty hefty, a lot of image data. So yeah, you might want to be careful when you're copying, but it's good to know you have that ability. And certainly with lists specifically, I think a list would have to be like, I don't know, hundreds of millions of elements big to be even to even approach something that might start threatening RAM limitations. So anyways, okay, I've gone deep into the realm of tangential speculation of interesting but not that important things. So it's a good question. Let's see. Let me see. Now I just want to rent more memory from Amazon. Yeah, that's the thing, right? Do they even make less than 8 gigabyte RAM computers these days? Good question. All right, y'all are funny. Okay. Hopefully everybody's good. So that's copying. I want to show a quick sort of use case for copying. Let's say I have a list equals, I'll call this my list. My list is a list, and so I'm going to pass my list to my function, and my function is going to, actually, I should have given it a different name. It's going to take in a list of numbers and return a list with all the odd numbers removed. So I could say for num in list, if num is odd, the way I'll test if it's odd is say mod 2 equals 1, then I will remove it. I'll say list dot pop num. Range len. I'm going to do I. Oops. So I'm going to iterate through the indices actually. So sorry about that. And then we'll return list. I might get an error here. Well, I removed I removed all the even numbers. Okay. Great. Thanks. All right. I'm trying to think of a way to do this with the things that I've taught you thus far, so I'm limiting myself to those things, or things that are close, because I know we haven't covered pop. Let me do something easier, something simpler that's going to involve less. So let's just say, let's just remove. So pop when you don't pass in an argument, just removes the last element. So we'll just say my function just removes the last element from the list, and I'm just going to return list. Okay, so I have my list, I print it out, I've got my function, my list goes into my function takes in list, it performs list pop, which removes the last element, and then returns the list. The thing is, this list and this list are the same. So when I go to access my list, it got altered by the function. This is something you always want to avoid. And it's something that you, in my experience, always can avoid. Again, right, like copying may be expensive. It's possible that you're working with constraints on your RAM. It's possible that you're duplicating information arbitrarily. Could not be an option, but in this case and in most cases, copying would be an option. So if I could copy this list, perform the pop on the copy, then my original data would be safe. So if I say list equals list.copy, there we go. And you can see my original list was untouched. So the context for using copy is usually when you pass a list into a function. If inside the function you intend to mutate the list you passed, you should always copy it. And I always like to override it, right? By the same name. I'll use the same parameter name. So this overwrites the list internally in the function. It doesn't mess with this list. It just says, you know, LST, the identifier LST now refers to that copy rather than the original, right? And that's what I like to do, because if I intend to mutate it, I don't even want access to the original, usually. There are cases where if I allow myself to use copy, and I can do the other example for num in list dot copy, so I could iterate through a copy and then remove from the original, or I could iterate through the original and remove from list copy equals list copy, right? So in this case, it might be beneficial to keep the original one around so I have something to iterate through. And then we will do that. List copy. There we go. Right. So I can do that mutable remove behavior, but I need one list to iterate through, and I need another list, two separate lists for this operation, right? So rather than tripling the data, in this case, I'll use the original data for the part of the function that I'm not going to mutate it on, and then I'll use the copy to do all the mutating on, right? But if I don't need two distinct copies of the list, if I don't need the original in addition to something to mutate, I will just rename it the same thing. That way I don't even give myself access to the original in the function. That way I can't screw things up. So that's my thing that I like to do. Okay, cool. I can't believe an hour has already gone by. Let's reconvene at 13 after the hour. Okay, cool. We're back. Hopefully everybody had a good break. Got a little stretch. Somebody's saying that my glasses are glow in the dark. No, they're not, but they are extremely cool and very shiny. So, yeah, they're just short. Somebody's also saying this isn't big data. Data mining. Look at data points in the trillions. How much RAM would we need for that? I'm not exactly sure. I don't know if you need terabytes of RAM for that. You might. Is that how that works? Data points in a trillion. Depends on how many bytes each data point takes up too. If each data point takes up 1 byte, then you need trillions of bytes, which is, I think you're in the terabytes range. Yeah, but if it takes up multiple bytes, then you need, I guess, multiple terabytes. So, the solution for that is definitely to start with the biggest computer that you can drum up and figure it out from there. So once you guys are working on computers that size, I will be but a distant memory in your long past from when you were first learning Python, and list manipulation will barely be a concern at that point. So. All right, cool. If anybody's got any questions, feel free to throw them in. I'm gonna move forward, but yeah, we'll go from there. Okay, I think maybe we'll just save this breakout for next time. So we've already kind of implicitly covered a lot of this. This is all about loops and kind of implicitly lists as well, because you can kind of see we were using loops to traverse, to iterate through lists. Often we'd call that traversing a list, walking through a list, right? Accumulators are something that I've alluded to, but haven't dove into all the way. Boolean flags, we'll be talking about list accumulators. Boolean flags are just accumulators for Booleans. They just have their own special name. We'll be talking about loops as filter and the 3 keywords break, continue, and pass. So I talked about pass. I find this funny. In our material and every other programming material I've ever encountered, break, continue, and pass for a language that has these 3 keywords, which a lot of languages do have these 3 keywords, pass is always taught with break and continue. But I find it funny because break and continue are things for loops, and pass is not. Pass is just a thing for kind of anything. We talked about this before. Pass is valid code. It is, it's not like this is invalid code. Like Python's going to yell at me if I do that, but Python sees pass. So that's valid code. Python sees that as valid code, but it just doesn't do anything. And the reason it's important is because certain times Python needs there to be code somewhere, and if there's not, it freaks out a little. It'll throw an error. So you can just say pass, which is like saying yes. I know there's no code in there. Don't worry about it. And then I'll get to break and continue at the end of this lesson as well. Hopefully we'll get that far. Okay, so traversing a list. So no big thing here. Oops. Why did I make it so big? 4989. Okay. This is all that's meant by traversing a list. We put a list in the iterable portion of the for loop and we iterate through it. That's all that's meant by that. Cool. Let's do this breakout. I'm just going to screenshot it. Actually, no, I will. We'll do it this way. I realized I should be doing things this way. Oh wait, we totally did this one. Did we do this one or did we do it? We did one like this one. Yeah, we did one like this. So I'm gonna just make this, make a little template for you all. Oops. So code, and you'll uncomment the lines, and then in a comment, result. So the result will stay commented, and then the code will be your code uncommented. Oh, and I'm sorry. These will need to be tabbed back. Okay, there we go. Oh no, non-ASCII characters. Sorry, don't copy that string. Okay, wait 1 second. I'm gonna fix it. Okay, now you can copy that string. I fixed it. And I'm gonna put 3 minutes on the clock. Okay, that's time. I only see a few answers, so go ahead. I'm going to give another minute on this. If you're stuck on one, you can move on to the next. Okay, cool. Go ahead and get your answers in. Whatever you've got is fine. Okay, so I'm going to go through and solve these. How would you index to get the value 8? So let's print x sub 8 is at index 0, 1, 2, 3, 4, 5, 6, 7. X sub 7. And that gives me 8. How would we slice to get 5, 3, 1? So 5, 3, 1 is going to be a slice. It's going to be a reverse slice, so I know I'm going to need to do negative 1. So 5 is at index 4. Let me just see if that starts me at 5. It sure does. And this is actually going to be negative 2, 5, 3, 1, just like that. So start at 4 and go backwards in steps of 2. I guess we don't, gosh, I had this idea to structure things this way for breakouts. We totally don't need the result there because it's telling you what result you should get, right? Okay, cool. How would you replace the value 4 with the value 10 using indexing? Okay, so this one's a bit interesting. So if we do x sub 0, 1, 2, 3, if we print that, we'll see that's going to be index 4. Or excuse me, element 4, right? So we can actually assign a value to that index. I can just say 10 like that. And then if I print x sub 3, now it has 10 instead of 4. Let's do a before and after on that. And then let's just change it back to 4 in this case we need that. Cool. So this is called item assignment. I didn't mention it earlier, which I'd forgotten we had a breakout that was gonna cover it. I don't think I mentioned this earlier. If I did, I was brief about it. I debated it, but this is not something that you use a whole lot. So I just kind of wanted this to come up naturally, just so I didn't overload you with like all the list features all at once. I will be showing a system later that will kind of go over that a little bit, or we'll cover it again. And there's not much more to know about that. I mean, if you use an index to a list, you can assign to it like it was a variable. It's called item assignment, and that's how it works. Sorry if that was a gotcha though, but anyways, how would we slice the list to get hello and 85? So that's in this nested list here. So that's this was index 7, 8, 9. So that's at 9. So let's do print x sub 9, and that should give me that inner list there. Oops, should give me that hello. Okay, so then this is a list. X sub 9 is a list, so we can just slice it from the beginning to index 2, and that'll go up to not including the last index. How would we add the value 42 to the end of the list? X dot append 42. There you go. All right, cool. For loops, we've gone over syntax. Traversing a list is just a fancy way of saying just putting a list in the for loop to iterate through. Yeah. Let's do another breakout. Let me kind of try to reformat this. I'll give you a, I'll do this. We'll move that out there just so you can mess with it. There you go. So one thing I want to be clear about this is asking you to write a function. You could write the function like this with the variable inside of this, but we actually don't want to do that. We want this to, you want your function to take in an argument, and you can use this as an example argument. So write your function in such a way that it takes a list or a collection as an argument and will do what's being described with that argument. remember you're going to want to write a function that will take in the char list as an input into the function and return excuse me. In this case, we're not gonna return. We are printing. My bad. Okay, cool. I'm going to show a solution here. So sorry that hopefully that wasn't too misleading. I saw some people using print in their, as a kind of the conclusion of their code to print things out. I am so used to training people away from that. I saw it and I was like, remember, we're going to be returning. And then as soon as I said that, I was like, oh, this problem statement totally just states print the letter if it's a value. So this is an exception to that rule. So given the following list of letters, we're creating a function that goes through each letter and prints the letter if it's a vowel. So let's call this vowels. I'll say def vowels will take in I could call it list, but it could actually work on a string exactly the same. So I'm going to call it text because these are characters. I'm going to call the function with vowels like this, char list, lost list. And we'll say for ch in text, if ch in, and we can check for membership in a list of vowels, A, E, like this. We could check for membership like this, or we could check for membership in a string as well. A, E, I, O, U. So if the character is in A, E, I, O, U, we can print character. Okay, O and I. So let's look at a slightly different way. I'll do the return way. So let's make a list, and we're about to talk about accumulators here. So this will be an accumulator. We've seen a few of these before, and then we'll just return the list, right? So I have an empty list. I append all the vowels that are all the characters that are vowels, and then I print where I call the function, right? Print O and I. There we go. So similar sort of thing. In general, you're going to write your functions to return things. I need to go back and rewrite this one so that it's oriented around, building a function that takes an input and returns a value. Okay. So this example obviously gives has a helper function that just tells us true or false if a letter is a vowel, and it's checking for membership in a list of vowels. I did a string of vowels either way. Either way, it'll work. Okay, we've got another breakout. Maybe I'll save that one for tomorrow. Let's see what's this one. Yeah, I can't believe time just flies, for me at least. I don't know. Hopefully it's going by well for you guys, but it just seems like we run out of time so fast. So I'm going to move on to accumulators. So accumulators are important. I can't really overstate that. They're very important. I remember when I was when I was learning in the material that we were going through in the class that I was in at Galvanize when I was learning to program in the web development immersive. It was material somewhat like this, and there were a lot of different concepts being covered and introduced and explored, and then accumulators came and went, and it was just another topic in a sea of other topics. And I didn't really get at the time like how central this was. It wasn't until like a few months later I was working on a project, and it was a big project, and I was still in Galvanize, and I was still a student. I mean, it was a big project, and I was a few days into it, and I realized like all I was doing was writing accumulator patterns. Like, you know, every problem that I had to solve, I was like figuring it out from scratch, inventing the solution. And what I realized, I kind of looked back through my code, and it was just one accumulator pattern after another. It was like a few dozen functions at that point. You know, few, maybe 1,000 or so lines of code that I had built up. I don't remember. It was a lot. And it was just one accumulator pattern after another, and I was like, oh, that's weird. I didn't realize it was that important. And it was kind of funny because it was just me doing problem solving. Just every problem that I faced, I would just arrive at, oh, well, if I started something empty, I could go through this thing and collect all the correct elements. And I had just been inventing the accumulator pattern kind of over and over and over again. And it was that moment that I realized like how central this idea is. It is everywhere. It's not absolutely, there are problems that you will solve, there are functions that you will write that don't involve an accumulator pattern. Absolutely, you'll do that. It's not uncommon, but at least for the kind of coding that I've done, it seems like honestly most of it I'm writing, you know, most of the time I'm writing a function, that function houses an accumulator pattern or two of some description. The accumulator pattern is a relatively simple concept. It's got a few parts to it, but it's a relatively simple concept that can get relatively complicated. They can get pretty nuanced. Accumulators can get fairly complicated. You can have accumulators inside of other accumulators and things like that, but it's a simple idea. That's what's going on here. So just the name is fairly descriptive of the process. So I'll just read through this. An accumulator can be thought of as a running total that is held in a variable. It's a little reductive, but gets you most of the way there. The accumulator pattern, in a nutshell, we initialize the accumulator variable. I'll say usually we start it at 0 or empty, depending on the type. We can accumulate onto basically any type. So we can accumulate into an integer or a string or a list or a float, whatever. I guess we can't accumulate on none because none is a unary value. When we accumulate with a Boolean, we call it a Boolean flag pattern. It's just it's the analogy of an accumulator for a Boolean, but it's a little different because Booleans only have two states. So Boolean's flags also don't really come up that much. So if they seem a little weird, it's something you can kind of keep in the back of your mind and you don't have to sink into right now. So we initialize the accumulator variable usually at some empty-ish or zero-ish state. We repeat some process with a loop of some kind and modify the accumulator variable accordingly. Either we add to it or subtract from it, or maybe we look at something and decide not to modify it. Yeah, various operations that we alter the accumulator, or not. And then when the repeat part is finished, when the above loop terminates, the accumulator will have the correct value, or a value that you can take to the next stage of the program and then turn that into the correct value, or whatever. However you want to look at that. So we can accumulate. This is going to go through and basically just show accumulation onto various types that we've talked about. So integer and float accumulation, I'm just going to consider the same thing because it's just like you're altering a number in some way. We could call that numeric accumulation. So let's just say num equals 0, and what if I'm feeling a little, let's have something to iterate through. I'll say source for will be a list. I'm just curious about this. I'm going to say for I and source, print I squared. Yeah, okay, I can work with that. So let's do this. Let's accumulate the sum of the squares in this list. So let's call this sum of squares. So in order to accumulate the sum of the squares, I can say sum of squares equals, plus equals I squared, and then sum of squares. This is a great candidate for a function. Let's call the function sum of squares, and it will take in src, and let's say def sum of squares. We'll call this iterable. Take in an iterable, and I need to find a different name for this variable. Let's call it total, and we're going to return total, iterate through iterable, return total. Okay, let's turn that whole thing into a function. Cool. Let's make a variation on this. I promised we would work with ranges. So let's play around with a range. So let's do a variation on this called sum of squares in range, and this will take in a number, and we'll just do range. Let's do 1 to n plus 1. That's what happened. Okay, we'll do that. 385. Okay. So that's a variation of that. So I just wanted to give a variation using range so you could see how we commonly use range. So in this case, I wanted to start at 1 and go up to and including n. So that was an arbitrary decision, so I just decided to do that. So here's a couple just kind of standard accumulator style functions. You know, we have our function and we have our accumulator target. The thing being accumulated on, I'll often call the target. The thing being iterated through, I'll often call the source. So the range is our source of things to iterate through. And then the target is the thing being altered in the accumulation, right? That's being targeted. So these are nice and simple accumulation, numeric accumulations. These are both integer accumulators. Let's look at another integer accumulator, one that you've seen me do before. Def factorial. Factorial will take in n. And I'm just going to call this prod equals 1 for I in range 2 to n plus 1. We'll say prod times gets I and return prod. And let's do print factorial of, let's say, 4 and 5. Bingo. Here we go. So factorial, there's another accumulator pattern for you, just a simple numeric accumulation. So you can see, even just with numeric accumulation, there's a bit you can do. You can write a few interesting functions. I showed you list accumulation. In some ways, I think list accumulation is kind of even easier if you know how to append, like, you know, the world is your oyster with sticking stuff in lists. You know, you can just keep appending to a list. Check conditions. Often it's common to check a condition that will tell you what to what to add to the accumulator, or how to add to the accumulator, or if you should or shouldn't add to the accumulator, things like that. So that's an accumulator. Another common one is just a counter. You know, if I wanted to count, let's say I wanted to count numbers that were divisible by 3, for I in range, let's say 45. I'm going to stick with my Hitchhiker to Guide to the Galaxy theme and go for 42. We'll go for I in range 42, if I mod 3 equals 0. If I mod 3 equals 0, counter plus gets 1. We want to start counter at 0, and then let's just print counter. Counter. Why can't you use the sum method on these lists? Well, we could do this. Let's do this with the sum. So sum is a function, by the way, not a method, because it doesn't have a dot. Well, I mean, it's technically kind of everything is kind of a method. That's sort of a whole other. We're opening up a can of worms with that. We could do list accumulation here. Since we're doing plus equals, we could do list accumulation. So that's the thing, is when you say, why can't we do sum on these lists? The answer is because those weren't lists. But we could write this as if they were lists, and it would work the same. Or we could rewrite this for the accumulator targets to be lists, and it would work the same. So let's just rename this list so it's nice and semantic. So you can see 385, 385. So we could use the sum function, but we still have to do basically the same accumulation to get those elements into the list in the first place. Cool. All right. So yeah, there's our counter. So evidently there are, 14 numbers between 42 and, or 0 and 42 that are divisible by 3. It's probably, I could probably figure out a quicker mathematical solution for that, but that's a way to do it, that particular problem with a counter if you wanted to do it that way. Oh boy, that is a good stopping point. We've got like less than 2 minutes to go, so I don't want to try to cram anything into 2 minutes. Everything that's worth talking about is going to take more than 2 minutes to really talk about. So we'll wrap up here. Let me stop the recordings and we'll open up for questions.